Welcome back to Sec 1 Geography. Today we are opening Unit 3, Water. And we are starting with a question that sounds strange. The Earth is covered in water, so why do billions of people face water shortages? By the end of this video, you will understand exactly why. You will know the water distribution data, all 8 water cycle processes, and how human activity changes the cycle in ways that increase flood risk. Let's begin. Before we look at any numbers, let's think about this for a moment. If you look at Earth from space, it is blue. Oceans cover roughly 70% of the surface. Water is everywhere. Yet over 2 billion people live in countries facing significant water shortages. That seems like a contradiction. It is not a contradiction, it is a distribution problem. Most of Earth's water is salt water we cannot drink. Of the fresh water that remains, most is locked away in places we cannot easily reach. The fraction that is actually available for human use is astonishingly small. That is what this chapter is about. Here is the plan for today. Look at the roadmap on screen. Chapter 1 covers Earth's water distribution, the key statistics, including the figure that trips students up most on WA Question 1. Chapter 2 goes through all 8 water cycle processes and the 2 energy sources that drive them. Chapter 3 looks at water surplus and water stress, their definitions, causes, and examples, including why Singapore is water-stressed despite receiving heavy rainfall. And Chapter 4 covers human interference, how deforestation and urbanization alter the water cycle and increase flood risk. The 3-mark deforestation question in WAQ3 is the highest mark single question in this set. By the end of Chapter 4, you will know exactly how to answer it. Before we go further, let me flag the 3 mistakes I see most often on this topic. Mistake 1, stating 3% as the answer for accessible freshwater. 3% is the total freshwater on Earth, but almost all of it is frozen. The accessible surface freshwater figure is much lower. We will get to the exact number shortly. Mistake 2, describing a water cycle process instead of naming it. WA, question 2 asks you to name 4 processes. Water falls from the sky, describes what happens but does not name the process. Precipitation is the name, names get marks, descriptions do not. Mistake 3, listing the outcome of deforestation without the causal chain. Deforestation causes flooding is an outcome statement. It scores 0. 3 cause-effect links, explained in sequence, score 3 marks. We will build that chain step by step in Chapter 4. Here are the exact WA questions this video prepares you for. Look at the screen. WA question 1 is 1 mark. State the proportion of Earth's water that is accessible surface freshwater. WA question 2 is 2 marks. Name 4 processes in the water cycle. Half a mark per process, 4 processes required. WA question 3 is 3 marks. Explain how deforestation affects the water cycle. That is 6 marks in total from 1 video. Every one of these questions is addressed directly. Let's start with Chapter 1. Chapter 1, Earth's water distribution. This chapter is all about data. There are 4 numbers you need to know, and one of them causes the most common mistake on WA question 1. Let me show you the drill down that makes this impossible to confuse. Look at the cascade on screen. This is the drill down from all of Earth's water to the tiny fraction we can actually use. Start at the top, 100%, all water on Earth. Drop down, 97% is salt water in the oceans. Far too salty for drinking or farming without treatment. That leaves 3% as freshwater. But look at the next level, approximately 2% of all Earth's water is frozen in glaciers and ice caps, locked away in Antarctica, Greenland, and mountain ranges. We cannot access that directly. That takes us to groundwater, about 0.7% of total water, stored underground in aquifers. Difficult and expensive to extract in most regions. And then, at the very bottom, accessible surface freshwater, rivers, lakes, and wetlands, approximately 0.1% of all water on Earth. That thin sliver at the bottom of the cascade is the freshwater that feeds our rivers, fills our reservoirs, and supplies our taps. 0.1% of all water. Remember that number. Let's look at the full breakdown on screen. I want you to spend a moment reading these figures. Saltwater, 97%, glaciers and ice caps 2%, groundwater 0.7%, soil moisture 0.2%, rivers, lakes, and wetlands, the accessible surface freshwater approximately 0.1%. And below that, water vapor in the atmosphere at less than 0.01%, negligible. Notice the key figure in the highlighted row, 0.1%. That is the WA question 1 answer, not 3%, not 0.7%. The question asks specifically for accessible surface freshwater, the water in rivers and lakes that is actually available for human use. The answer is approximately 0.1% or less than 1%. Write that down, underline it, it will appear in your WA. So why is so little freshwater accessible? Look at the 4 reasons on screen. Glaciers and ice caps hold the largest share of fresh water, but they are frozen solid. We cannot drink glacier ice without melting and transporting it, which is impractical at scale. Groundwater is stored underground in aquifers. It can be accessed by drilling, but it is expensive, slow to pump, and in many regions the aquifers are deeper than existing technology can reach affordably. Soil moisture is bound in the soil itself, not available as flowing water for drinking or irrigation. And water vapor in the atmosphere is dispersed over the entire planet in microscopic quantities. What remains, the rivers, lakes, and wetlands, is the fraction that the water cycle keeps replenishing and redistributing. But replenishment is not uniform. Some parts of the world receive far more precipitation than others. That uneven distribution is why some countries have water to spare and others face constant shortages. Let's test what you have just learned. Look at the table on screen. I want you to fill in the missing proportions from memory: saltwater, glaciers, groundwater, and accessible freshwater. Then answer the bonus question: what percentage of Earth's water is accessible, surface freshwater? Pause the video now. Take 2 minutes. When you are ready, unpause and I will show you the answers. Welcome back. Let's check the answers together. Saltwater, 97%. Glaciers and ice caps, 2%. Groundwater, 0.7%. Accessible surface freshwater, rivers, lakes, and wetlands, approximately 0.1%. And the bonus answer, approximately 0.1% of all Earth's water is accessible surface freshwater. That is the WA question 1 answer. Look at the red call-out box on screen. The common mistake is writing 3%. That is the total freshwater figure, but most of that 3% is frozen. The question asks for accessible surface freshwater. The answer is 0.1% or less than 1%. These 2 figures refer to completely different things. Make sure you read the question carefully. Excellent. Let's move to Chapter 2. Chapter 2, the water cycle. The water cycle is the continuous movement of water between the ocean, the atmosphere, and the land. It is driven by 2 energy sources and involves 8 named processes. By the end of this chapter, you will be able to name all 8 and explain what each one does. WA. Question 2 asks you to name 4. Any 4 is fine, but knowing all 8 gives you maximum flexibility. Before we go through the processes, let me tell you what drives the whole cycle. 2 energy sources. Look at the screen. First, solar energy. The sun heats the surface of the ocean, lakes, and the leaves of plants. This heat is what converts liquid water into water vapor and drives it upward into the atmosphere. Without the sun, there would be no evaporation, no transpiration, and the cycle would stop. Second, gravity. What goes up must come down. Precipitation falls because gravity pulls water droplets down from clouds. Surface runoff flows downhill because of gravity. Groundwater moves slowly through rock toward the ocean, pulled by gravity. Every downward movement in the water cycle is gravity at work. Now, the 3 upward processes, driven by solar energy. Evaporation, liquid water on the surface of oceans, lakes, and rivers, is heated and turns into water vapor, rising into the atmosphere. Transpiration. Plants release water vapor through tiny pores in their leaves called stomata. In dense forests, transpiration adds enormous amounts of moisture to the atmosphere, often as much as evaporation from the soil surface below. Evapotranspiration. This is not a third separate process. It is the combined measurement of evaporation and transpiration together. It is used in water budget calculations, particularly in forested areas where both are significant and difficult to measure separately. Now look at what happens once that water vapor is in the atmosphere. Condensation. As water vapor rises higher into the atmosphere, the temperature drops. Cool air cannot hold as much water vapor as warm air. The vapor cools and changes state, converting back into tiny liquid water droplets. These droplets cluster around tiny dust and salt particles in the air, forming clouds. Condensation must happen before precipitation can occur. No clouds, no rain. Precipitation. When water droplets in clouds combine and grow heavy enough to overcome air resistance, they fall to the Earth's surface. The form depends on the temperature at cloud level and on the way down. Rain in warm conditions, snow in very cold conditions, sleet when it partially melts, hail when ice pellets form and cycle multiple times within the cloud. Look at the sequence on screen. Evaporation and transpiration move water upward. Condensation forms clouds. Precipitation brings it back down. That is the core of the cycle. Now, when precipitation reaches the land surface, two things can happen. Look at the screen. First, infiltration. Water soaks into the soil and rock. How quickly this happens depends on three things: the type of soil, the amount of vegetation cover, and how much human development has changed the surface. Sandy soil allows fast infiltration. Clay soil is much slower. Vegetation cover helps because plant roots create channels for water to follow, and leaf litter on the surface slows down the rate at which rain arrives. But now look at the right panel. Impermeable surfaces, concrete roads, tarmac car parks, rooftops do not allow water to pass through at all. Zero infiltration. This is the word you need for urbanization, coming in Chapter 4. A natural land surface, high infiltration, water soaks in slowly and steadily. A concrete surface, zero infiltration, water cannot enter the ground at all. That difference between natural and urbanized land is the foundation of the entire flood risk discussion. When water cannot infiltrate, either because the ground is already saturated from heavy rain or because the surface is impermeable, it flows across the top of the land as surface runoff. Look at the diagram on screen. Surface runoff flows overland, downhill, into rivers and streams. It gets there fast. A natural hillside covered in vegetation might take hours or days to get rainwater into a river through slow infiltration and groundwater movement. The same hillside covered in concrete gets it there in minutes through surface runoff. The faster water reaches a river, the faster the river level rises. Fast rising rivers flood. Below the surface, groundwater. Water that does infiltrate deep into permeable rock is stored in aquifers underground. It moves very slowly, sometimes taking decades or centuries to travel through rock to reach a spring or river. Groundwater is a vital reserve for many countries, but it replenishes slowly. Over-pumping depletes it faster than it can be refilled. Now look at the complete water cycle diagram on screen. All 8 processes are shown together. Let me walk you through one full cycle starting from the ocean. Solar energy heats the ocean surface. Evaporation. Water vapor rises. Trees on land release vapor through transpiration. Both contribute to evapotranspiration. The vapor rises and cools. Condensation, forming clouds. Precipitation brings rain to the land surface. On the land, 2 paths. Some water infiltrates into the soil. Groundwater flow carries it slowly underground back toward the ocean. The rest becomes surface runoff, flowing across the land into rivers, reaching the ocean much more quickly. That is one complete cycle. Every process connects to the next, and the whole system is driven by the sun pushing water upward and gravity pulling it back down. Commit this diagram to memory. WA. Question 2 asks for any 4 process names from this cycle. You have 8 to choose from. Chapter 3, Water Surplus and Water Stress. Now that we understand the water cycle and the distribution data, let's look at what happens when supply and demand fall out of balance. Some places have more fresh water than they need. Others never have enough. Look at the comparison table on screen. 2 situations, water surplus and water stress. Water surplus, available freshwater supply exceeds the needs of the population. Countries like Canada, Brazil, and Norway have high and reliable rainfall, low population density relative to their land area, and abundant rivers and lakes. They have more water than their populations demand. Water stress, demand meets or exceeds the available supply. Saudi Arabia receives very little rainfall. It is a desert environment. Egypt depends almost entirely on the Nile River, which originates thousands of kilometers away in countries Egypt does not control. Jordan is one of the most water-scarce countries in the world. Look at the impacts row in the table. Water surplus countries benefit from lower water costs and sufficient supply for all uses. Water-stressed countries face rationing, expensive treatment and supply infrastructure, food insecurity if irrigation fails, and conflict between different water users. Agriculture, industry, and domestic consumers all competing for the same limited resource. The key line at the bottom of the screen, water stress is about supply versus demand, not just about rainfall. That is the critical insight for the Singapore case coming next. Now, here is the most important geographical insight in this chapter. Look at the Singapore case on screen. Singapore receives approximately 2,400 millimeters of rainfall per year. To put that in perspective, London receives about 600 millimeters. Sydney receives about 1,200 millimeters. Singapore gets twice as much rain as Sydney, 4 times as much as London. Yet Singapore is classified as water-stressed. How? Look at the 4 reasons on screen. Singapore's land area is only 704 square kilometers, one of the smallest countries in the world. There is very limited space for rainwater catchment. Most rain falls on urban surfaces and drains into the sea before it can be stored. The population density is over 7,000 people per square kilometer, one of the highest in the world. Demand per unit of land area is enormous. Singapore has no major rivers to provide a continuous freshwater flow. And critically, Singapore has no natural groundwater aquifers. There is nothing stored underground to draw on. Result, even with heavy rainfall, Singapore cannot capture and store enough water to meet its population's needs. This is water stress caused not by a lack of rain, but by a structural imbalance between supply and demand. This understanding is why Singapore has invested so heavily in its water management system, which we will cover in the next video. Chapter 4. Human interference with the water cycle. Humans change the water cycle in 2 main ways covered in this course. Both increase flood risk. Both affect the same part of the cycle, infiltration and surface runoff. Let's go through them in order. First, deforestation. When trees are removed for farming, logging, or urban development, 2 water cycle processes are immediately reduced. Look at the diagram on screen. On the left, the natural forest. Water vapor rises from the leaves as transpiration, a significant source of atmospheric moisture, especially in tropical forests where this process is continuous and large-scale. Now look at the left side of the forest canopy. Before rain even reaches the ground, it is intercepted by the leaves and branches. The canopy acts as a buffer, slowing the arrival of rain, allowing time for evaporation back into the atmosphere, and letting water drip more gradually to the soil below. This is called interception. On the right, the stump. No transpiration, no interception. Rain arrives at the bare soil directly, nothing to slow it down. These 2 changes to the water cycle, reduced transpiration and reduced interception, set off a chain reaction. That chain is the 3-mark WA answer. Look at the causal chain on screen. This is exactly how to structure WA question 3. Each arrow is 1 mark. Step 1, trees are removed. Transpiration and interception both decrease. That is the first mark, a named process change and the immediate effect. Step 2, without tree roots and leaf litter, the soil is no longer channeled and protected. Rain hits bare soil hard and directly. The infiltration rate decreases, less water soaks in. Step 3, with less infiltration, more water has nowhere to go except across the surface. Surface runoff increases dramatically. That water reaches rivers much faster than before. Rivers rise more quickly, and flood risk increases downstream. 3 steps, 3 marks. Each step connects a cause to an effect. The mistake I want you to avoid is jumping from step 1 straight to the outcome. Deforestation causes floods. That skips the mechanism entirely. The marks are in the mechanism. Write the chain. Second, urbanization. When natural land is replaced with an urban environment, the key change is the introduction of impermeable surfaces. Look at the comparison on screen. Natural land allows rain to soak into the soil, high infiltration. The water moves slowly through the ground, arriving in rivers gradually and steadily over hours or days. Now look at the urban panel. Roads, pavements, car parks, and rooftops are made of concrete and tarmac. These materials are impermeable. Water simply cannot pass through them. When rain falls on an impermeable surface, it cannot enter the ground. Every drop that falls becomes surface runoff. It does not have the option to infiltrate. It flows immediately into drains and drainage channels. The word impermeable is the key to this whole explanation. Learn it, use it. It is the mechanism that connects urbanization to flood risk. Because infiltration is blocked by impermeable surfaces, all rainfall becomes surface runoff. That runoff is channeled through storm drains and concrete channels directly into rivers, arriving far faster than natural runoff would. Look at the chain on screen. Impermeable surfaces. Infiltration drops to zero. Infiltration drops to zero. Mfall, all rainfall becomes surface runoff, is channeled rapidly into rivers. Mfall, rivers receive large volumes of water very quickly. Urban areas experience significantly more flooding than equivalent natural land under the same rainfall conditions. This is why city planners increasingly look at solutions like permeable paving, green roofs, and urban parks, surfaces that allow at least some infiltration and slow the journey of water to rivers. There is an additional effect worth knowing. Urbanization also removes vegetation. Less vegetation means less transpiration. Less moisture returns to the atmosphere. Combined with impermeable surfaces, a newly urbanized area becomes dramatically more flood-prone than the natural land it replaced. Now let's put both together. Look at the 3 panels on screen. Panel 1, original rainforest. Transpiration is active. Interception slows rainfall. Roots channel water to infiltrate. The river downstream is low and steady. Panel 2, the forest is cleared. Transpiration stops. Interception gone. Bare soil begins to lose its structure. Infiltration starts to decline. Runoff increases. Panel 3, a city is built on the cleared land. Now we have deforestation and urbanization combined. No transpiration. No interception. No infiltration. Impermeable surfaces everywhere. Every millimeter of rainfall becomes immediate surface runoff, reaching the river in minutes. The result, flooding becomes frequent, severe, and predictable. This is exactly the scenario in Worksheet C. C, Section C, rainforest cleared, city built, flooding follows. You now have the geography to explain why. It is time for your practice pause. Look at the WA question on screen. Explain how deforestation affects the water cycle. 3 marks. Use the 5 keywords shown: transpiration, interception, infiltration, surface runoff, flood risk. Write 3 separate cause-effect points. Each point should explain what changes and why, not just the final outcome. Aim for 3 to 4 sentences. Pause the video now, write your answer. When you are ready, unpause and I will walk through the model answer. Welcome back. Let me go through the model answer with you. Look at the 3 points on screen, each with their mark annotation. Point 1. Deforestation removes trees, which greatly reduces transpiration. Less water vapor enters the atmosphere from plant leaves. That is 1 mark, a named process with a stated effect. Point 2. Without tree canopy, interception is lost. Rain hits bare soil directly. Without roots to protect and channel the soil, infiltration decreases. That is the 2nd mark. 2 linked effects explained causally. Point 3. With less infiltration, more water flows across the surface as surface runoff, reaching rivers much faster than before, increasing the risk of flash flooding downstream. That is the 3rd mark. Surface runoff to flood risk, with the mechanism explained. 3 points, 3 marks. Look at the call-out at the bottom of the screen. Cause linked to effect equals a mark. Stating the result alone equals 0 marks. The examiner is looking for the chain, not the conclusion. Let's fix the 4 most common mistakes on this topic before we close. Mistake 1, WAQ1, writing 3% for accessible freshwater. The correct answer is approximately 0.1%. 3% is total freshwater, most of it frozen. Read the question carefully, it asks for accessible surface freshwater. Mistake 2, WAQ2, describing instead of naming. Water falls from clouds, no mark. Precipitation, mark. You must write the process name. 8 names are available: evaporation, transpiration, evapotranspiration, condensation, precipitation, infiltration, surface runoff, groundwater flow. Pick any 4. Mistake 3. YTUAQ3, writing only 1 point for a 3-mark question. 3 marks always requires 3 distinct points. Students write 1 excellent explanation and stop. Write 3. Mistake 4. Y. WAQ3, outcome without mechanism. Deforestation increases flood risk. Tells the examiner you know the result, but not why. Explain transpiration, then infiltration, then surface runoff. That is the mechanism, and that is where the marks live. Let's close with 5 things to carry away from this video. 1. Approximately 0.1% of all Earth's water is accessible surface freshwater, not 3%, that is total freshwater, mostly frozen. 0.1% in rivers, lakes, and wetlands is what we can actually use. 2. The water cycle has 8 processes: evaporation, transpiration, evapotranspiration, condensation, precipitation, infiltration, surface runoff, groundwater flow. 2 energy sources: solar energy drives water upward, gravity drives it back down. 3. Water stress is about supply versus demand, not just rainfall. Singapore receives 2,400 millimeters per year but is still water stressed because of its tiny land area, high population density, and absence of rivers and aquifers. 4. Deforestation chain: trees removed. Phi, transpiration and interception, decrease CI. Infiltration decreases XE surface runoff, increases CI. Flood risk rises. That chain is 3 marks. 5. Urbanisation chain: impermeable surfaces. Y. Infiltration blocked. All rainfall becomes surface runoff. Rivers rise rapidly. Flash flooding. Here is what to do next. Complete your viewing guide and revision note. Then work through the worksheets in order. I covers the water cycle, B covers distribution, C covers human interference. Finally, attempt the WA practice, 6 marks, 12 minutes, no notes. Subscribe for the next video, Singapore's water management and the 4 national taps. See you there.